We start. I close. So we can start the afternoon session. And the first speaker is Bernard Deconinck, and he will talk about the instabilities of large amplitude Stokes wave.
Thank you, Alberto. It's great to be back here. I think it's been about 12 years or so since I was in this room. I'm also going to start this talk by saying this is the last time I'm going to give this talk. I've been giving this talk too many times, so you can hold me to that. But it fits in very well with the theme of the workshop. Let me start by acknowledging a whole bunch of people. A lot of these were students at the University of Washington when this work was done. Some of them are on the audience. Olga is here, Levent is here, Ellie is here. I think that's it. And then different funding organizations and fellowships. When people ask me, why do you study water waves? I show them pictures like this. And then I ask them, why don't you study water waves? Just for the sake of making sure, well, I think you want me to tell you where these things are, so I'll tell you where these things are. This is off the coast of Peru. And these are the only waves that I'll say much about, namely the ones over here that are really one-dimensional, and they're not feeling the effects of anything going on in the other direction. The other patterns are clearly all three-dimensional waves, and I'm not going to say much about them except maybe one sentence at the very, very end. This is off the coast of one of the islands in the north of New Zealand. That's a drone shot. This is a very old picture, black and white, of the Army Corps of Engineers building a mock-up of what became the San Diego harbor. And when the Army Corps of Engineers makes a mock-up, this is big. If a person was standing here, that'd be about this big. So this is a few Olympic-sized swimming pools large. For me, this is the interesting part. For them, this is the interesting part. Because if you want to unload a cargo ship, you don't want your ship doing this. This is an hour north of Bordeaux. This is Ile de Ré in France. I was in Bordeaux. I was in Bordeaux, just visiting, but I was in France for 3 months. Unfortunately, I didn't make it there in May, which is when these waves tend to appear. Okay, but water waves are obviously very fascinating. Let's talk about some aspects of them. This is the Euler water wave problem, which Massimiliano also put up this morning. That's not Euler, that is Kelvin, who was, according to Craig, the first one to actually write this complete set of equations. So this is a free boundary value problem. I'm looking at a incompressible fluid that is governed by Laplace's equation. Of course, there's no cross direction, so this is going to be the two-dimensional Laplace equation, and then I have a one-dimensional surface. Oh wait, that's the wrong button. I have the surface right there, and that is really what I want to know about. Where is this surface, and how does it move? And I'm doing this for a flat bottom, this time at least, and sometimes that bottom will be at infinity. So I have this Laplace equation, which sounds easy enough. That's a linear problem, but I have to solve this Laplace equation in a domain that I don't know, right? That makes this hard. I have a very simple boundary condition at the bottom that just says that I'm not losing any water through the bottom, but then I have two far more complicated nonlinear boundary conditions at the unknown surface, the kinematic condition and the Bernoulli equation, basically the balance of pressure at the top, which we already discussed this morning as well. Because this is a very complicated free boundary value problem, there's been a lot of different approaches reducing this problem to just a problem dealing with the surface variables. Okay, I'll mention a few. Zakharov-Craig-Salem approach right there, which has been very important in lots of theoretical approaches, some of which I'll mention. And the Alvarez-Focas-Musermani approach is fairly recent, and that is an approach that we have been using a lot in our group, especially for small amplitude waves. And then when it comes to large amplitude waves, which is what's in the title of the talk, then we've been using the conformal mapping approach, and I will tell you why right now, why that is the only thing that we can use. Okay, so let's think of this as a very complicated dynamical system. How do we study dynamical systems? The first thing we do is we look for fixed points, then we linearize about these fixed points and examine their stability and hopefully try to piece together the information. So this is far more complicated in that setting, but I'm going to more or less follow that same approach. We're going to look for traveling wave solutions. I'll go to a moving frame so that these are now equilibrium solutions, stationary. I will linearize about those fixed points, get a linear stability problem, a spectral stability problem, and then I'll have a couple of linear operators that I need to examine the spectrum of, which will tell me about the different instabilities that these waves are susceptible to. And if you're here if you want to hear about stable waves, then I hate to disappoint you because everything's going to be unstable except flat water, but you'll all agree that's not very exciting. You can write down specific equations that these traveling waves, these Stokes waves, satisfy using the Ablis-Foucault-Muslimani approach. They can be written as the solutions of this problem right here, which is you can think of as some kind of a nonlinear condition on some Fourier coefficient. But it is really quite horrible, right? It is non-local, non-linear. There's the differential right there. And then we have the surface elevation inside of this trigonometric function, which is maybe not a surprise given the dispersion relation for the water wave problem. If you use a conformal mapping approach, you find the Babenko equation, which is, well, maybe it looks more compact. It's also quite complicated because this operator k hat in there is minus the derivative of the Hilbert transform. So it's, of course, also non-local. And everything that we do will be non-local because you have to deal with Laplace's equation at some level. I'm not going to focus on the Stokes wave. We heard a great talk this morning about three-dimensional Stokes waves. Again, everything in this talk will be one-dimensional. I'm using the convention of my student Vishal Basan that says we should talk about one-dimensional and three-dimensional waves, and there is no confusion. So we'll do that. So Nekrasov and Livicivita proved that the formal calculations of Stokes, who just calculated a few terms, that these were the first terms of a convergent expansion, so proved rigorously the existence of these Stokes waves. And Struck, this was an infinite depth, and then Struck added finite depth. Okay, so these Stokes waves exist. Stokes already had a conjecture that there was a steepest Stokes wave, and that this wave had a 120-degree corner at the crest. Okay, that took a lot longer to prove. Toland proved that there was a steepest Stokes wave, and then Amick, Franklin, Toland, and then Plotnikov proved that for all depths, the steepest wave indeed does have this 120-degree corner. Okay. If you plot these waves, so this is done using numerical bifurcation theory. So this line right here corresponds to flat water, and on the vertical axis you have amplitude. You get bifurcation branches starting at points dictated by the dispersion relationship. And so then I have the solution plotted for different points on this bifurcation branch. I rescaled all of those solutions to have the same amplitude, because if I didn't do that, you would only see the last one. Okay, but in shallow water, and I will define in 5 minutes what I mean by shallow water, what you get are these, for larger amplitude waves, you get these profiles that very much look like Deconinck waves that you would see in a KdV-like equation, for instance. Okay, if you go to what I will define to be deep water, then as you go up the bifurcation branch, you really have to go very high before the solution starts visibly being different from a regular trigonometric linear wave. Okay, last preliminary thing that I need. See, that blue box is green on my slides, okay. The problem is Hamiltonian, shown by Zakharov and some other people. So what you could do is you could take this Hamiltonian, and for every one of these Stokes waves that you have, you can plug it into the Hamiltonian and you get a number. And then that number oscillates as a function of the steepness of the Stokes wave. Now, I should point out that I'm plotting this on a log scale of the limiting steepness minus the steepness of the wave I'm looking at. If I don't plot this way, then everything, all these oscillations are bunching up at one point and you wouldn't see anything. Okay, so we're stretching this out to be able to look at this properly. Let me very briefly talk about the blue box. It says capillary scale in there. For the steepest wave, we have this 120-degree corner. Okay, if I have this 120-degree corner, capillary effects will matter. Okay, capillary effects want to not have that corner. So there's going to be a range of steepnesses. If I become sufficiently steep, I cannot ignore, as I am, the capillary effects. Okay, and a back of the envelope calculation will tell you that you can go to past the second extrema of the Hamiltonian and still not, and for ocean waves, capillary effects still don't matter. The other curve, by the way, the red curve, there is the velocity of the wave, which is also oscillatory as you approach the steepest wave. Okay, we'll come back to these plots later. So let's talk about stability. So let's start. My title says large amplitude waves. I'm going to start with small amplitude waves. So our Stokes waves, they are periodic waves. We can write down a Fourier series. For instance, right there, you have a Stokes wave. The velocity has to be expanded as a function of the amplitude as well. And once you do that, you can start talking about, maybe small amplitude waves, and we'll actually use the same setup to also talk about large amplitude waves later on. So how do we look at the stability? We take our Stokes waves. I'm already in a moving frame, right? So these things have no time dependence at all. They're not even translating. Okay, I look at these things and I perturb them to order epsilon. Rho. Rho is my small parameter, and I have a perturbation, and then I have higher order effects which I'll ignore. So let me talk about this part right here. If you linearize around your Stokes wave, you get a linear problem that has coefficients that are not dependent on time because I am in this moving frame. Okay? Because my coefficients are not time dependent, I get to do separation of variables, and that's where the e to the lambda t comes in. Okay? So that's just a separation constant. I now have a problem with linear operators that have periodic coefficients because my Stokes wave and all of its derivatives are periodic. So now I do a Floquet-Bloch decomposition, which leads to that e to the I mu x. I'm doing 2 pi periodic waves, so I have my Floquet exponent sitting between -1/2 and 1/2. Okay, using the scale invariance of the problem. So plugging all of that in, I get a generalized spectral problem right here. So I have this R mu operator that I have to deal with, but it's basically a spectral problem. And now I'd like to know about the spectrum of this problem right here, analytically if we can, numerically if we can't. Okay, so are these waves stable or unstable? Let's again start with small amplitude waves. The first results using formal perturbation expansions are from Benjamin and Whittam. Benjamin and Whittam, using entirely different types of calculations, found that waves in deep water were susceptible to what we now call, maybe I shouldn't get too close to these guys, are susceptible to the modulational instability or the Benjamin-Fair instability as we call it now. Okay, so it's called the modulational instability because if you turn on these perturbations, what's happening to a periodic wave is you start developing what looks like beats. And then other things happen beyond that. But the first thing that really happens is things start looking like they're forming beats. In the spectral plane, what you get is, so this is the complex lambda plane, that lambda being that separation constant, my spectral variable. I have this cross at the origin. Anytime something goes into the right half plane, I'm going to have an instability because that means something is going to grow exponentially in time. Okay, so Benjamin and Whittam proved that you had this cross at the origin. If your dimensionless depth was greater than 1.363, which is the root of some equation involving hyperbolic functions, which is not a surprise given the dispersion relationship. So that is what I call deep water. If my dimensionless depth is greater than 1.363, I call that deep water. I have the Benjamin Fear instability for small amplitude waves. If I am more shallow than that, I call that shallow water. Okay? So those are formal calculations. It took a while for the first rigorous results. Bridges and Milke in 95, using spatial dynamics, proved that this cross at the origin was there. Okay? They could only do that in finite depth. You have a loss of compactness problem as you go to infinite depth. That problem was solved using a different method by Gwynn and Strauss in 23, so quite recently. One of the really great things for me about this problem, I mean, this is an old problem, right? We were talking about Stokes and Kelvin and so on. And these are very classical questions. But a lot of the progress on the stability of surface water waves really has been made in the last 10 years, as you'll see with some of the other references I'll put up here. Okay, so we now have Benjamin Fear in finite and infinite depth. And then He and Yang provided an alternative proof, also using Evans function. Also only valid in finite depth using Evans functions. Here's some numerical results that I did with Katie Oliveras. So if you compute the spectrum in some part of the plane around the origin, you find this. So this is the spectral plane. If you zoom in on these different things, imaginary axis here, real axis is here, it looks like you have these three straight line segments, two off the imaginary axis and then one on, on the real axis and one on. That's not what happens. If you zoom in on this, you see that you have a figure 8. Okay? If you zoom in on these other ones, you have an oval. Okay, that's interesting. So we knew, because this is deeper than 1.363, we knew that we had to have this cross at the origin. We didn't know that that was going to be part of a figure 8. Okay? I have a very strict chair, and I'll skip these results for the sake of time. So Ryan and I did some asymptotics, but in 22, Birdie, Maspero, and Ventura, 2 of them are in the audience, rigorously proved the presence of this figure 8. Okay, and so they provided an approximation to it. So this figure 8 that was observed numerically is actually there in the problem, shown rigorously. Same authors also showed a little bit later what happens at the critical depth exactly equal to 1.363. That's a harder problem. And you find that there's still a figure 8, but it's more narrow. Okay. Benjamin Fear, the modulation of stability, was such a big topic in the stability literature for water waves for so long that there was this common belief, as you can read in the classic book by Ablis and Seeger, for instance, that if you didn't have Benjamin Fear, then waves were stable. So if you were in shallow water, water waves were stable. This is not true. So in the same paper with Katie, what we were trying to do at that point was we're trying to show that this is the maximal growth rate, so the largest real part in the spectrum for a fixed amplitude wave. And as a function of dimensionless depth, we were trying to show that there was nothing. And then at 1.363, we got this growth rate. That's the plot we were after. That's not the plot we found. We did find that, but we also found out that there's something else. Something else, which is obviously dominant for shallow water because there is no Benjamin Fear. But then even if you have Benjamin Fear, it could still dominate for a little bit. And now we're going back to these plots. The first one you've seen. So that's in deep water. And I've already shown you that this one right here gives you this oval. This is shallow water, less than 1.363. Okay, so now there's nothing on the or close to the real axis. If I zoom in on this one, I'll find an oval. If I zoom in on this one, I get an oval. If you squint, maybe there's something else there. There's another oval. 3 ovals. 1, 2, 3, infinity is the obvious conjecture. So we conjecture there's an infinite number of these things. They're numerically very hard to find. A lot of people miss them in the literature. And the reason they're very hard to find is, the Benjamin Fear figure 8 is parameterized by a Floquet exponent that sits, between 0 and, some 0.3 or something. Okay, it's a large range of Floquet exponents. If you parameterize these isolae, Italian word for island, if you look at them as parameterized by the Floquet exponent, they are parameterized by a range of Floquet exponents on the order of 10 to the minus 4. So if you were just running your computations for 100 equally spaced Floquet exponents, you're likely to miss everything. That is what most people did. That is what we did for a while, except we got lucky occasionally. So they're very hard to find, and it really helps if you know where you have to look for them, which is where the dispersion relationship helps. Ryan and I were able to do some asymptotics. We had a research retreat in my group at some point. Her and Yang proved the rigorous existence of the first one, the one closest to the to the real axis. When Ryan and I did the asymptotics, we found a few, but we couldn't keep on going because to go to the next isola, you need to go to higher order in the perturbation expansion, because that's when the first real correction to that perturbation expansion shows up. You can't just immediately go there. You can't skip the lower orders because there are imaginary corrections at the lower order, so you do have to do that work. And then while we were at this research retreat, we had a whole agenda for what we were going to do at this research retreat. And then Alberto sends me a preprint, and then that whole agenda went out of the window, and we just started reading this preprint. I think this is a magnificent piece of work. Berti, Corsi, Maspero, and Ventura proved that in infinite and finite depth still open, right? They gave a rigorous proof, and I'll state it colloquially, this is not 100% accurate, gave a rigorous proof of the existence of an infinite number of isola. Okay, and then for every isola, they actually gave an asymptotic expansion. And many key differences, but one of the key differences is really exploiting the Hamiltonian structure of the problem, allowing you to get to those real parts of the eigenvalue contributions much more efficiently than we were able to do. So I need to get to large amplitude waves. So let me conclude about small amplitude waves. It's just been an overview so far. Of course, there's always open problems. But I would say that the core problem of looking at the stability of small amplitude waves in deep and in shallow water is basically now well understood, both at the analytical and the numerical level. Important things to prove, I think, have been proven. And so that's an incredible amount of progress. So let's talk about large amplitude waves. And by large amplitude waves, I mean waves that are very close to the 120-degree wave. Okay. We only have numerics. So actually, I'll make a little bit of a comment about non-numerical results, but we only have numerics. And we use the conformal mapping approach, and I'll tell you on the next slide why. And so far, I'm only going to tell you what's happening in the vicinity of the origin and things coming out of it, which means I'm not going to tell you about the high frequency instabilities for now. So the numerical method, and this is the reason why we're using the conformal mapping, is due to Anastasia and Sergey. And here's the main problem, right? If you're looking at waves that are very close to the steepest wave, you're close to having a corner. And if you're going to have a Fourier representation for such waves, then, well, you're going to need a ton of Fourier modes. And a ton, for us, could be as many as 10 to the 7. Okay, so we actually do numerical runs with 10 to the 7 Fourier modes. And it matters. You can't just stop early. The results are affected. The stability method that we would typically use is we would build, we have an operator equation, right? You would truncate that representation of the operator, and you get a large matrix equation. Okay, so if we use that approach here, we would end up with matrices, complex floating point matrices that would have 10 to the 14 entries that we would have to store. That's simply not possible, right? You can't even do this on a supercomputer. Okay. What allowed us to do what we're doing, what you'll see in the next slides, is we have this matrix-free approach where we don't need to store the entire matrix. We can get away by just storing the action of the matrix on a vector. So now we're down to 10 to the 7 entries storage again, as opposed to 10 to the 14. That was really... This is why we're using the conformal mapping approach, because we don't know how to do that using any of the other approaches. Okay? Okay, you've seen that picture before, and then here's the illustration of using a lot of Fourier modes to try to approximate the corner. Of course, we never quite get at the corner. That we've talked about. So the picture that's not on here is the picture that only has the imaginary axis for flat water. But if you increase the amplitude, you get the Benjamin Freer figure 8. There's high frequency stuff as well, but I'm ignoring that. Okay, so you get the figure 8. You increase the amplitude, the figure 8 gets wider, larger. So the instabilities grow. Eventually, the tangents at the origin co-align, and we get this hourglass shape. The next stage, the hourglass breaks off, and we end up with a Benjamin Freer remnant above the real axis and one below, of course, because of symmetry. They separate more. They separate more and almost vanish. But then something else happens at the origin. There's another crying collision happening at the origin, and two eigenvalues come off, and go onto the real axis. That grows, and you get this oval, still the Benjamin Freer remnant. This grows more. All of these plots, the first I've shown you, the first two rows, all have the same scale. I didn't rescale anything. From here to here, I'm rescaling because otherwise I'm going to lose stuff. Okay, and now these are all again not scaled. So this is the same plot as that one. This oval becomes larger and deforms to a bean, and these remnants of figure 8 get actually reabsorbed into it. This bean eventually becomes a figure infinity. The figure infinity is very different from the figure 8. The figure 8 exists for a range of steepnesses. The figure infinity exists for an isolated steepness, namely the extrema of the first extremum of the Hamiltonian. Okay. I've also marked 2 points here. In green, that corresponds to a perturbation of my problem, an eigenfunction of my problem that is coperiodic with the Stokes wave. So it's 2 pi periodic. In red, I could have marked the red here and here as well. That corresponds to a perturbation of twice the period of the Stokes wave. So a subharmonic perturbation, okay, of larger period. Okay, this is very interesting because this has the largest growth rate. So this is the most unstable. Let's follow this. So I'm going to forget about that. Just follow this. You get that. And we can go through the whole movie if you want, but really the important thing is subharmonic is most unstable. Still true, switch. Over here, the coperiodic one became the most unstable. Okay, still true, switch. So we've seen a number of switches, more than I've shown you here, of this subharmonic of twice the period and the coperiodic perturbation. Okay, I don't know why that's happening, but it seems to recur. I should also say the steepest wave occurs for steepness 0.14109. We're very close to the steepest wave already. So these numerical runs are very costly. I've just shown you the life cycle, or a cycle of different pictures that happens as you increase the steepness of what happens to the stability spectrum, or the instability spectrum, I should call it. Everything that you've seen happens again. So for large amplitude wave, for large amplitude Stokes wave, this is the most important message. That's why it's big and blue. So specifically, all of this, this happens, and then we've been following this. Let's actually keep on focusing on the origin. And if you do that, then eventually that happens again. There's another figure 8 getting born at the origin, and it does all of this again. And again, we've seen 3 cycles.
So you see many of these isolats.
Yeah, so let's say you get a whole range of, we've seen up to 3 of them separating from the origin and going off to the right. And left, of course. Okay.
And do they go to infinity or they?
I'll talk about that. So this is actually all of the plots I've shown you of the oscillations of the Hamiltonians are cartoon plots, because if we showed you the actual oscillations, there's a damping factor of 10 to the minus 4 from one oscillation to the next. So you would barely not see anything, right? It's very fastly damped. But you have this green region starting from 0 steepness or amplitude up to the first extrema, other than 0, of the velocity. And everything that happens, all those pictures have shown you that happen in that range of steepnesses, recurs as you go from that first extrema of the velocity, the red curve, to the first, first maximum, next minimum. All those pictures repeat. And again. And beyond that, it's hard to compute. Figure 8s from one cycle to the next are hard to compare because, as I said, the figure 8s live for a whole range of steepnesses. But we could compare the hourglass for each of those cycles because the hourglass exists at an isolated steepness. And also we could look at the widest figure 8, namely the most unstable one. Okay, and that's what's done here. This is in green the widest figure 8 and the hourglass figure 8 for the first cycle that I've shown you before. Here's the same for the second cycle. Now, I don't even have to do anything quantitative here. You can see that these are different. Okay? But if I compare second and third, those look very similar. And if we can quantitatively compare that, notice that this is very high amplitude, very high steepness. That's the same plot, we can compare them by, for instance, looking at the real part as a function of the Floquet exponent. And you have here, I think, well, the one that's clearly different, the blue one is for the first cycle. And then the red and blue one are for the second and third cycle, and they're right on top of each other. And there's a difference of, it's not written on here, but I believe it's 10 to the minus 3 between them. So the phenomena that we see recurring past maybe the first one seem to settle down very, very quickly. The eigenfunctions show much more difference, right? So you have same color coding as there. You have eigenfunctions for the first occurrence, second and third. The eigenfunctions show differences. But notice that all of them show a modulational character. Okay, so there's a clear envelope to them. So even though we're very far past the original Benjamin-Fehr instability, the modulational instability, all of these figure 8s really show that similar character. I'll skip talking about the oval, harder to compare. The figure infinities are very easy to compare, other than the fact they're hard to compute because they already occur for very steep waves. But if we compare the first and second figure infinity, the difference is already 10 to the minus 3 if you overlay with real and imaginary parts as a function of Floquet exponent. How much time do I have? Ooh. Really? Okay. All right. I'll spend some time on this. So there is the limiting steepness. Actually, that number is now known to about, Ali, do you remember 25 digits or something? Yeah. So, there's a lot of accuracy known for that number. And as you've seen, 0.14106, not 9, as I said, a lot of the plots we were having were, very close to that already. Two conjectures, they're in red because they're not ours. And also, if these are not true, then everything else that I'll say is wrong. But we believe these are true. We believe that the Hamiltonian has an infinite number of local extrema, and there's actually a paper that comes that Eric told me about, that comes very, very close to proving that. We also believe that the velocity has an infinite number of local extrema.
What does it mean, very, very close?
So Eric can correct me on what I'll say next, but basically, so it's denser Buffonian toland, right? Buffoni denser toland. So they prove that either this is true or there's another possibility that they can't rule out. You want to add something to that, or? Okay, all right. But I don't believe there's a similar result for the velocity. So these are all in black and are all a consequence of the numerical results I've shown you. This is addressing your question. Anastasia, in her thesis, which only dealt with coperiodic perturbations, already showed a numerical plot matching her data very well, showing that the growth rate goes to infinity at a square root rate as you approach the maximal steepness. Okay, as you incorporate more perturbations, including the subharmonic ones, obviously you're going to go at least as fast. Okay, now that's interesting because it seems to indicate that the if you wondered about the dynamics of the steepest Stokes wave, then that problem seems to be ill-posed, right? And there's a lot of discussion about well-posedness for the Euler equations, but those well-posedness results don't deal with stationary solutions. They deal with, starting with corner singularities and things like that. It's, we've tried to match with the literature, and I'm very, very confused by it because they need an internal angle that is less than 90 degrees for well-posedness. So in other words, the evolution of this is well-posed. The evolution of this, they can't say anything about. I'm confused by that. Okay, but that's about maximal growth rate. We believe that there's an infinite number of Benjamin Fehr figure 8 instabilities. These come out of the origin, and upon their formation, they exist for a range of steepnesses. And then they detach. We also think there's an infinite number of these figure infinity instabilities. They correspond to the steepnesses for which the Hamiltonian has an extreme low value. Okay, and those are isolated values, so not a range of values. These figure 8s and these figure infinities alternate in their occurrence. I've shown you the cycle. Another way of saying this is the extrema of the Hamiltonian and of the velocity are interlaced. Okay. Going back to following that one isola drifting off to the right that prompted your question, it looks like the most unstable mode for very large waves is either coperiodic or subharmonic with twice the period. It sounds like the kind of a statement that there should be a nice physical explanation for it, but I don't have it. But it is, I don't understand why twice the period is special in this case. We believe there's an infinite number of these interchanges. We've seen 3. Let me actually go back before I talk about current and future work. When Katie and I did the numerics, we first showed a figure 8 and so on. It took a while, and then people picked up and started proving the presence of the figure infinity. The figure 8 in the Benjamin Fehr figure infinity, figure 8, and then also the high frequency instabilities. Okay, when we found these high amplitude results, I was thinking it was going to be 20 years or so before there were any analytical results, because from an analysis point of view, at least you had a starting point that you well understood before, because we understand flat water. Okay, when you want to do the analysis for these near extreme waves, your obvious starting point is a 120-degree wave, which is not so well understood. Okay, waves that are near the 120-degree wave can actually have steeper than 120-degree parts close to the crest. So there's lots of complications there. But in the last year and a half or so, Dmitry Polanovsky and some co-authors, they've pioneered a hybrid approach. So it's not fully rigorous, not fully analytical, because the input for their approach are the numerically computed Stokes wave coefficients. Okay, but using that, they're able to show all of the presence of all these perturbations, all these bifurcations that we've seen here, right? So things happening at extrema of the Hamiltonian, things happening at extrema of velocities, at period doubling bifurcation points, and so on. Okay, so that went a lot faster than I had expected that to happen. So that's really great. Some things ongoing and that should be started. Ellie is now working on the instabilities of large and near extreme waves in finite depth. Okay, so everything I've shown you for large amplitude waves, I'm not sure if I emphasized it enough, was for infinite depth. Okay, now you bring another parameter into it, complicates things. One thing that is more complicated now is that when you're dealing with small amplitude waves, the distinction between deep and shallow water is pretty straightforward, Benjamin Fear. Okay, when you're dealing with very large amplitude waves, that becomes far more complicated because the amplitude of the wave now starts to impact, what previously was, deep water. So that is far more complicated. And if you thought that some of the pictures I've shown you were exotic, once you bring in the extra parameter, there's much more stuff that happens actually, and many more interesting bifurcations. So that's forthcoming. And then there's also been a lot of literature on transverse instability. So the Stokes waves are one-dimensional. What can we say about perturbations that are three-dimensional? Okay, so Wynn and Strauss, soon some others have, there's a lot of excitement there, great progress. We started looking at numerical only for now at the instabilities of fully three-dimensional waves. So not one-dimensional Stokes waves, but wave patterns, hexagonal patterns, diamond shapes, and so on, and looking at the instability spectra that you get for those things. Now, that is obviously more complicated because now your spectra will not be a collection of curves in the complex plane, but there will be regions in the complex plane. Okay. And last, I'll say a little bit about surface tension. So we've done very little with this, but Eric and Sun have a recent work that shows that those high frequency instabilities that I showed you, and that have been proven. Birdie, Corsi, Maspero, Ventura showed there's an infinite number of these for the gravity wave case. If you include surface tension, that's not true. Any amount of surface tension gets you down to only a finite number of these high frequency instabilities. So it's actually a great result, I think. And I'll throw up a bunch of references and I'll stop there. Thank you very much.